right, we are recording for our review. So let's start by just asking what people want to focus on. I will get up the slides from the second slide deck, because I'm pretty sure that's what we're going to want to focus most of our attention on. But if anyone can just peruse the study guide and come up with some questions.
Everything from the second slide there, or just the stuff?
Just the stuff that's on the study guide. Definitely not everything. We will eventually cover all of everything, but we cannot start there because we have not lectured over a large chunk of it. And I don't want to do that. I'm nice, but not recess nice. I'm mean, but not play in the street with no supervision.
What about that? I feel like that falls somewhere in there.
What's nice is, as someone who is not your parent, I can't tell you what to do with your time, as long as it's not distracting in class. So if you decide to take a nap, you just can't be a snorer.
Oh my God. It's allergy season, man, come on.
It's always allergy season. Unfortunate. I'm allergic to half my family being cats. Waiting for my laptop to boot because for some reason it has to put itself to sleep. But where do we want to start?
Can we start with I just had it. I was just looking at it. Where did it go?
It's recess.
It went to recess, yeah. I'm reading through the study, I'm trying to find the word again. I just had it in my, policy, iterative policy evaluation algorithm.
Yes.
Let me go over that really quick.
Yes.
To Jay? Yeah, Jay.
There. All right. Iterative policy evaluation. So this is this algorithm. It's on slide 23. But it's also described right ahead of that. So we talked about using Bellman's optimality equation to calculate or to find an optimal policy. So first you have to figure out how good is the current policy. Are there any improvements we could make to the current policy? So we need to figure out how good it is. So for every state, we are going to calculate based on just the possible successor states, the value of this. So you would start by doing a sweep of the state space. You're just going to say for each state, what is the value of being in that state? Or for every state action pair, what is the value of being in that state and choosing that particular action? So that's all this equation is really saying, is finding the expected value of being in a particular state. Once we figure out the value of a policy, which is just saying at the very beginning of this game or task, whatever it is, what do we think the average value is going to be? What the expected value is going to be for this task, given the policy that we have. So you do not have to start thinking about an optimal policy. You can start with a random policy or a policy that makes no sense. And as you evaluate that policy, it will become apparent what a better policy will be. So we can go through figuring out how good that policy is. And we found the application of this being this grid world game that we talked about. So what is the value of being in each one of these states? Given that the policy is we're going to move randomly. The episode is terminated when we're in the top left or bottom right square. You can also think of the value in terms of how many steps on average will it take you to get to one of these terminating squares, the top left or bottom right. If we start in square number 1, for instance, we found via iterative policy evaluation that it's expected to take 14 steps to terminate, assuming that we're using a random policy. So how that worked is we said, all right, we're going to solve this iteratively. Rather than analyzing this fully, we're going to go step by step and just update the value of being in this state based on this kind of stepwise update. We're gonna look at the value of the states that we reach, the cost of that being the one action that we took. Every time we make a move, it's going to cost us -1. So the update for this basically said, wherever we are, we're going to, with 25% probability, end up, down, left to right. If we hit a wall, we don't go anywhere. So from spot 1, if we move up, we stay there. Analyzing that, we find that we have value -1, no matter what we do. But some of those threads are going to terminate and lead to the episode ending. So that leaves us with, we're gonna do a search of the state space and figure out, all right, if we're here, we're already here. There's no reason for us to move from one of the terminating places. So that value is still 0 because the episode has ended. But everywhere else, no matter where you move, you get the value 0 plus the 1 that it cost you to move there. So that's why everything else is -1, regardless of where you go. Even if it's to a place that terminates the episode, it still costs you 1 to get there. So the average cost after one iteration for everything that's not just these couple spaces is -1. However, if you were in spot 1 and you happen to move left with your random policy, that episode ends. So you can now think of what is the average. It's going to cost us -1, but now depending on where we get, the expected value of being there is going to be bad unless we move left, which is still 0, which is why this updates less than this does after 2 steps. This is a better place to be than here, because after 2 steps, some of these episodes have ended. And this square, this number 2, is at least 2 away, so no matter what sequence of actions you take, none of those episodes have terminated. You just continue this process of iteratively taking the next step, the next step, the next step, and updating your costs as you go. And eventually, this converges to these values. But in order to do this, you have to recognize that there is some update value that is going to terminate this process. Once the state that has the largest update on a particular pass is less than 0.01, maybe we could say, then we are going to terminate. Because this process will get closer and closer and closer to this, but never get there. So we have to show that there is some level of update that is close enough to terminating that we're good enough, we're done. So this is iterative policy evaluation. We're just saying, we're just gonna initialize all these values to 0. Then we're going to explore, given that we're in this state, what are all the moves we can make? We can't make any because the episode is over. Given that we're in this state, we can move up, down, left, right. Since all of the state's values are 0, the average is going to be -1. You update for every one of these cells based on these values, then you replace this grid with this grid. Then you're going to sweep over every single state, update. And now this board becomes this board. Continue this process until the cell that changes the most is less than some threshold that you state when you begin, and that terminates the policy evaluation to values that are very close to this. Given that you have these values now, after having gone through iterative policy evaluation, which again, the encode for that is just right here. Then you go through policy improvement that says, given this information that we got, we are now going to improve the state of our policy by greedily selecting the best move given the available options. So the policy says act randomly. Policy improvement says rather than doing something random, just pick the one that is best, greedily. And as you do that, you are able to now truly improve the policy. So you go from a random policy to this policy, and as soon as you hit this policy, it's converged. This is the optimal policy. So it's a pretty quick process to be able to evaluate and then improve. Did that make sense? So there are further clarifications or questions on policy evaluation and policy improvement?
Think it makes sense?
What would it look like in some other situation?
Good question.
If I didn't give you exactly grid world, how could we apply this to something else? Anyone want to give me an example of something that you would imagine that an AI might have a policy for that could be improved to become optimal? Especially thinking about something with a limited state space, because as soon as you have lots of states, then this becomes very difficult to do.
Let's use our favorite example, tic-tac-toe.
Sure.
Because it's a very limited space and there's only so many possibilities that you could choose from.
Right. So applying this to tic-tac-toe, you would say, here is every possible board state in tic-tac-toe, every legal possible board state. You could then say, what is the value of making a particular move in that state space? What's difficult about using tic-tac-toe as an example is that an AI or another player gets to move in between your move and your next move. Let's imagine that it's always dictated. The other player is always going to move in the topmost leftmost available cell, so you can see it in advance. We can't really have a probabilistic view of this, or if we do, we need to do this long enough to where it incorporates it, which is very challenging. So if we're going to stick to this idea so far, let's imagine that we're just an agent that is in an environment that does not have anything outside of its own control. If you did this, then you could map every single move possible in tic-tac-toe. If you said the value of every state in tic-tac-toe initially is 0, except when you terminate it in 1, you would get a score of 1. If you terminate and lose, you get a score of -1. You could then say, if we're close to ending the game, if we have a random policy, and maybe I'm going to try to adhere to this, the O's are always moving in the top leftmost position that's available. Great, we're close to winning the game. We have as X 5 places we can move. One of them ends the game, one of them prolongs the game. If we are analyzing this particular position, we would say the value of a random policy in here, we're going to randomly choose where we're moving from here. So with 20% of the time we move there, or there. Right now, we have no sense of value to a state like this because the game isn't over. So if we wanted to come up with an expression for this, we would say with 20% of the time, we're actually going to get a reward of 1. 20% of the time, the rest of these we don't really know because they don't terminate the game. So basically, we can say the value of this state after a single iteration is this. So we're going to assign this value the next time this updates, everything updates to be 0.2. So now instead of this value being 0, we don't know, it hasn't terminated. We can see that according to a random policy, we win in 1 step 20% of the time. Now, once this is done, you can see that we either won the game or didn't win the game, but there are some number of states here that would lead us to, if someone makes a move, it leads to this state. When we placed this X and they placed this O, that got us here. When we iterate this for the second time, we're now going to be looking at this value being 0.2 instead of the game isn't over yet, it's 0. When we iterate this after we come up with the policy improvement, we will see rather than acting randomly, we should instead make the action that leads to this. So now this state doesn't actually have a value of 0.2 with a random policy, it should have a value of 1 with an optimized policy because we can win the game in 1 move. But if we are acting randomly, we're going to win in 1 step 20% of the time. 80% of the time, the game goes on. But if we continue to do this iteratively, we would start to see how good is it to actually be in the state if we truly play randomly? If we move here in the middle instead, how frequently do we win the game? If we move anywhere else, even if we still end up playing randomly, that doesn't mean we're always going to tie the game. Some of the time, we're gonna lose the game, some of the time, we're gonna win the game, but over a long period of time, you can actually get the value of this state, very much like we on the last slide got the value of these states after a long time of iterating through this. So you would take every single state in tic-tac-toe, you would look at every possible move that could be made, and then you would backtrack the value of each one of those with how likely it was that you were going to get there into the value of this state. Then you would overwrite that state with that value at the very end of all of that, and then do it again, and then do it again, and then do it again, until the value of a state that changed the most was less than some threshold that you stated at the beginning of the process. And then you would say, it's terminated. I know how well this policy performs. And then you release the new game of tic-tac-toe with an AI that acts randomly. You would be able to know at any particular state how likely that agent is to win the game. Do note, though, that that relies on a particular algorithm that the player, the enemy to your AI, so the player performs. As soon as there is something up in the air to that, we have to think of this in terms of a probabilistic analysis. In which case, the state that you end up at may change, which adds a whole new layer of depth to this that I don't really want to handle, especially ahead of an exam. I'm not going to throw that. That makes sense? Do we see how kind of tic-tac-toe relates to grid world with regards to how this algorithm might behave? One person nodding their heads? How confident are we in that? Can I explain that a little bit more? Is there? Seems like people don't really know where they are. That's an issue.
No,
Yeah,
and
I know.
it makes it
That's tough. That really means that there's some work to do here. To what extent, maybe some more thumbs, to what extent does the grid world example itself make sense? We understand how it's making these decisions, how we're coming up with these values. There aren't really any decisions being made. This is just an algorithm producing these values iteratively. Sweep the state space, update. Sweep the state space, update. Let's continue that process, and that maps to the algorithm we see here, which is basically sweep the state space, sweep the state space, sweep it, sweep it, sweep it until some change is less than some threshold that you state. For each state and our set of states, update the value of each one based on the associated math. It allows you to say, what is every possible successor state to this? How likely is it that we get to that particular new state? And then what is the value of that state when we get there? What is the value of, according to this policy, what is the value of that when we get there? Those are the steps for that. And then you just update the largest change that has been happening until that largest change gets less than the threshold stated. So it's not crazy in terms of its number of steps, but visualizing how it works for a different kind of example might be an important part of that. What else can I help with?
Looking at 2 on, what is the Monte Carlo exploring starts out with guarantee?
Yeah, so let's go down to exploring starts, which is right here. So it guarantees that we converge to the actual value of the value of being in a particular state action pair when we have an infinite number of samples. Great, how are we going to get an infinite number of samples? We do need to specify some particular state action pair that we're starting on. Because otherwise, there's no guarantee that once we come up with an associated policy that it's going to explore every possible move an infinite number of times. That's what we need in order to know for sure that this value is going to converge. The way that we know that we've solved the problem and have an optimal solution is that we continue to explore. And if there were a better path, it would reveal itself over a large sample. The law of large numbers kicks in, and even if we have bad luck with regards to maybe this is the single best start that we can make right here. But let's say the first time we do it, we just get directly into the bad square. That's going to bias Monte Carlo. It's going to backtrack all of this in a way that makes it look like this start was bad. Then we see this one, and maybe it goes directly to the green. This would make this look better than that, according to its one sample. And so if it's not infinitely trying this a bunch of times to get a real average on the value of starting here moving this way and the value of starting here moving this way, then the small sample bias might kick in and remove some possibilities that end up being the best possibilities just because of a poor start the first time we did it, or the first few times that we did it. So to converge for sure, we need to explore each start continuously. Over an infinite number of samples, we would start with each of these an infinite number of times. So what does it prove? It proves that we converge to the actual values. But we have to make sure that we are checking each state action pair an infinite number of times over an infinite number of samples. Obviously, we don't have an infinite amount of time to run this, but if you do that, then you let it go as long as you have time for, or until it stops making changes, and then you terminate and say, this is the best model that I can make. It's no longer exactly the right values, as we saw in the dynamic programming example, but when you don't know the state of the world when you start, we knew that in dynamic programming. We knew the entire state of the world. In tic-tac-toe, you know every place you can possibly move. So you can explore everything and come up with a model of the game without actually playing the game. Monte Carlo is useful when you don't have that. You don't know the full state space. You have to explore it. So we're never going to get a perfect value. We will just converge on the correct values with a larger and larger sample size. That makes sense. There was so much energy in this room, and then we started talking about reinforcement learning. And died. Everyone who asked for a nap wasn't joking.
And a snack.
Don't forget about my snack.
And the graham cracker, and I need the frosting.
Actually, we can hold the graham cracker. Just give me the frosting. That's a real first grade.
Squeeze it out, okay. So to paraphrase, essentially, exploration guarantees at some point that if we run it long enough, it will converge to what the values should be at any non-possible states.
Yes, but we rely on the law of large numbers for that, and we wouldn't be able to do that if we didn't explore every start enough such that the law of large numbers can't get. This isn't the only way to do this. In fact, we haven't talked about the other way to do this that is more frequently done, but this is one such way to do this.
And going down right below 2R to 2S, what are the benefits and detriments of an epsilon soft policy rather than exploring starts?
Yeah, so we get into the concept of an epsilon soft policy that says, this is very much like we talked about in the first slide deck, where with some probability, we're going to take the optimal action that we have found so far. With 1 minus that probability, we're going to be selecting some either random probability, or we can now weight them and select something based on, we're going to select the second best action according to our history with some other probability, a third probability, a third action with some other probability. But in general, you take the least likely one and say that there is some probability of each action being selected. And now we get that infinite exploration that we needed in order for this to work. But we now see that we are forever exploring. We're never going to stop exploring and start exploiting with any more likelihood than we already are. So compared to exploring starts allows you to now take the optimal actions, what seems like the optimal actions, once you have selected which place to start from. Here, you're building the exploration into the policy itself, rather than the exploration really just being, where did we start? Now the exploration is built into the policy where at any particular state, we could select the best thing that we've seen so far. We could select something random. If we select the something random, we're going to see, has our history with this action informed this, or am I going to learn something new running it this time? Maybe it makes me think this is better than history has taught me. That makes sense? Any further explanation for that? And there's something about the lecture that just destroys the spirit, huh?
I think it happens when it started reaching towards 4 o'clock, everyone's just like.
It's time for like sleep. Yeah.
It also doesn't help it's an exam review.
That's right. You have to remember this in a couple days. Be able to apply it in a couple days.
Who's posted away from that?
Yeah, right.
So for this class, is there still the rule that we have to get like a 60% on the exam to pass? Is that still a thing?
I don't think I stated that on the syllabus. Did I state that on the syllabus?
I have no clue.
I looked at the
It is
syllabus
there.
and it is not in there, but I
Yeah.
thought I would double check.
Yeah, I don't think the exams are really the major selling point of the class or the major outcomes from a game design class. So I honestly don't think it's as important as it has been when the purpose of that class is the exam material. This is meant to be augmentatory toward your game design, where you can make agents that learn in your games. That is cool, but it's not the main outcome from this. So I don't think that it should be the reason you pass or don't pass the class.
What was the percentage for the exams again? 10%? The
5% each for 2 exams,
Okay,
so very low.
okay, we're gonna do it, I can look, but.
She's already just.
Like I said, I don't think this is the most important part of this course. I think it's interesting material that when you understand it leads to the ability to create really engaging AI in your games. But it's not necessary to create a fun game. So it's a cool topic to explore. But yeah, I don't want to make a large portion of this class exams. It should be the decisions you make when you're making your games, the feedback you get from each other, and the quality of the ability to critically think and review games. That to me is much more important, which is why those are weighted higher. What else can I answer? Yeah.
With that in mind, Monte Carlo meaning we don't assume we know the state at all, we can't know the state. What's the big, when would we choose Monte Carlo over dynamic programming?
Yeah, when we can't understand the entirety of the state space, or when the state space is so large that the process of analyzing the entire state space it just won't converge. It'll take so long for policy evaluation and iteration to terminate that it's just not worth it. You can imagine, for instance, making a chess playing agent with dynamic programming, sweeping over the state space of every possible board state in chess. It probably won't finish before we perish. It won't have decided on how good is this policy by the time we perish. So it's just, it's not an easy way to optimize chess playing. So Monte Carlo is probably a better approach. That said, the state space is still so large that you would need a very large sample of Monte Carlo in order for any particular decision in that to make sense and to really start to have any intelligence whatsoever. So neither of these are going to be great for large games. We're going to want to temporal difference will be a bit better than Monte Carlo for that. Still not great because the state space is huge, but the real intelligence comes from combining reinforcement learning with supervised learning, being able to determine when are states similar to each other where we can transfer the learning from one state to another state. It doesn't look like it's exactly the same state, but for some abstract reason, these states are close to each other. The decision space is simpler, so we can learn from mistakes in one state when we analyze the other state. What's next?
Quick review of Bellman's equations use in evaluating policy.
Yeah, so let's back up to. Let's go right here. So here's the use of the Bellman equation. The idea was that we're using the existing state and every possible successor state based on this is every action we can take according to this policy in this state. And then this is every state that we could get to after we pick that action. So maybe this is probabilistic. This is something like I make a decision and then I flip a coin, and depending on heads or tails, I end up in a different state. It's also something like tic-tac-toe, where I make a decision about where to move, and my opponent has a bunch of places that they could choose to move, so I can find myself in any of those states after I get control again. So the Bellman equation just states, well, how likely is it to reach each one of these states? What is the value of being in each one of these states according to the best estimate that we have so far? We should use that logic to update the value of this state, which is exactly what we were doing in grid world. This is grid world. Yeah.
So the top arrow there is are the decisions that can be made, and
Yep.
then the arrows on the bottom are are branching not based on that decision, but just what could happen because of that decision.
Right.
Okay.
Yeah, so tic-tac-toe, this is the move you make, these are the moves your opponent could make. And then the state you end up back in, once control is returned to you, you're making the next decision about where to move. Two things have happened, the decision you made and the decision your opponent made. So here are all the possible game states at the next time you have control based on those two pieces of information. The decision you made, the opponent makes decisions based on the decision you made. So we're back propagating. Here's the probability of ending in all of these states. Here's the value of being in all of these states. All of that needs to be taken into consideration. Really, all we're doing is we're multiplying the probabilities of getting to each one of these and adding them. So it's just an expected value of, given that we're in the state, adhering to this policy when it comes to which action we select. How likely are we to get in each of these states? Backtrack all that information back to this state. Which is exactly, again, what happened in grid world, where we look at every possible successor state. If we're right here, we can either go here or here or here or here. Depending on where we go, there's the cost of traveling, and then there's the result of the value of the state we end up in. Backtrack all of that information to the value of this state, and we find that it updates to -1 instead of 0. Just do that for every single state in the state space, and then you have an update. But then you also have new values for some of these states. So we can update again, then we can update again, then we can update again, until they converge. That's exactly what's being described here. So this is what it would look like for a single state, looking at all possible successor states. the probability of ending up in those successor states, the value of being in those successor states. Adding all of those up and coming up with a value for this state, and you just do that for every state repeatedly. Until it converges. Seems like we're ready to take the exam. Either that or we're not ready to take the exam.
I personally feel not ready, like, I'm gonna do some more studying tonight and tomorrow night.
Yeah.
There's just so much here.
Yeah.
So are you gonna expect us to do it, or to be more like explain it? how-
More explaining than doing.
Okay.
So if you look at the kinds of questions that are on the study guide, the kinds of questions that are there are the kinds of questions that I will pull and ask on the exam. I can't state that I will take exactly question by question and throw them on the exam, but I would phrase them much like those questions. If I don't have a be able to solve, but a be able to explain, then I'm not looking for you to solve a system. I just want to see if you understand this process and be able to apply this process to maybe your own game that you make.
I'm probably gonna come by your office hours with more questions, cause I forgot that you posted the study guide until like 3 AM this morning. I was like, I don't have enough time to go through it and answer all the questions, see if I have questions.
That is fair. I will certainly be around in office hours. I have office hours from 11 to 12 and 1 to 2 every day. So feel free to stop by tomorrow or Wednesday before the class. And I can walk you through, answer any of your other questions as well.
I don't know about everybody else, but I could use a break.
With 8 minutes to go in class.
So I assume it's just gonna be a test on Wednesday, so it's gonna be like an hour long, they have to leave, or?
My plan is to lecture for a bit on
Okay.
Wednesday, so I want to get through some more content. We've only really had a couple of big lecture.
But it won't be on
Classes.
test.
Right, yeah, what I cover on Wednesday will not.
Gotcha, okay.
And we have 0.4 seconds to memorize what it covers.
I'll give you exactly.
Remember that you do get a note sheet, for those of you who haven't been, I mean, you all were in last quarter's class, but you can bring a note sheet, you can have anything you want on it, I'm not gonna check it, I don't really care. Whatever is useful to you, my goal is not to make you memorize a bunch of things, I'm not gonna have you regurgitate any of these equations. I'm not gonna have you solving too much. Most of it to all of it is going to be to what extent do you intuitively understand these concepts? So that is what I am going for. In a grad level class, I probably won't get to be able to solve these, but for undergrad, it's really just where do you apply it, when do you apply it, how does it work, why does it work? Those kinds of questions. What's the associated complexity? When do you have to worry about complexity? I have to worry about the complexity of this exam when I go write it.
Speaks of my complexities of talking to people.
Complexities of being in.
Don't worry, guys, it's worth 5%.
Yeah, it's not the end of the world one way or the other. That said, I would like for people to be able to do the best they do. So don't treat it like it's nothing, because the difference between good grades and bad grades on the exams will be about a letter grade difference in your final grade. But that's all it will be, is at most a letter grade. That's the difference between 100% and 0%. And if we know me, I like to throw extra credit on exams, or at least extra points available. That will probably be the case as well. Anything else I can answer with 5 minutes to go?
Honestly, no, my brain's a little bit fried from my other 2 midterms that aren't exams, they're projects.
Gross.
I've just been throwing myself at those and I'm just like kinda.
I have another midterm on Wednesday.
Say,
I'm gonna be doing 2 tests in one day.
which class got scheduled over top of this one?
Yeah.
All right, I'll go leave a really passive aggressive note on Tony's door.
Tony is usually, actually, no, Tony's probably already left, never mind.
He's probably.
Well,
That's
it's
why
not,
you
it's not the
discover it.
same time, it's just the same day.
Yeah.
Yeah.
I do apologize for that.
And
But I'll try
also
to
it's worth
separate.
a much larger chunk of our grades, so. I honestly do not know how much studied I will be for this one. The exam worth 25% of my grade is gonna take a bit more of my focus, unfortunately.
Probably working on your compilers.
That too. Anything else?
I feel like just having a long class on a Monday, it's just like 101.
Yeah. I
think it should be Tuesday, Thursday.
Yes, I was.
I kind of made that work, I would. Alright, I guess I'll stop the recording here. Hopefully that's enough to be useful to people. I'll get this posted and we'll go from there.